Welcome to the physics classroom. This is Elizabeth Hobbs helping you with the work and energy unit on Minds on Physics, and we are talking about specifically Mops9 work and energy conversions. And we've been talking about how the total amount of energy in the system is always conserved. Well, we lied to you because there's this thing called work, is force times the displacement. And there can be positive work, which would add energy to the system, or there can be negative work, which would actually take away energy to the system. So the amount of energy can change. So the amount of potential or kinetic energy can change in the system. And work, when a force is an external force, that's when it's a non-conservative force, and that's when the total amount of energy in the system changes. When there are internal forces, that's when the amount of total energy in the system will stay the same. So we've been working with roller coasters. If we ignore air resistance and friction, those are the things that are acting on our gravity, and that's an internal force, so the total amount of energy in the system is going to stay the same. Whereas things like friction and air resistance, those are non-conservative forces, so the total amount of energy in the system actually does change because work is being done in a positive or negative manner. And if you need the list of conservative versus non-conservative forces, go ahead and take a look at MOPS 5. Also, keep in mind that you can always go to the physics tutorial if this is not helping. And remember that you can press pause and rewind if you need repetition. I'm trying to go through these fast so the YouTube videos aren't long, and also that we can get through a lot of material quickly. So with the first couple of problems on MOPS 9, you really just need to look through the definitions and read through the problems carefully out loud to yourself. I know that it will help. So here, this is just a simple definition problem. An object's mechanical energy will not be conserved if, list all that apply in alphabetical order. Keep in mind all that apply. And also, we've been hammering in the difference between constant speed and acceleration and the first semester. Those kinds of things don't really apply as long as there is a force involved here. So keep in mind, well, here, let's go through the problems. Forces are acting upon the object are not balanced. Object is accelerating. The conservative forces are acting upon the object. Non-conservative forces are acting upon the object. Conservative forces are doing work upon the object. Non-conservative forces are doing work upon the object. Okay, so if the object is accelerating, that means that there are forces working on it, right? But we don't necessarily know if those forces are balanced or if there's displacement, so we can automatically eliminate B and probably automatically eliminate A on that one too. Okay, there can be acceleration, but it doesn't help us enough with the energy stuff. Then we've got non-conservative and conservative forces. Non-conservative forces are going to be doing work upon the object. Okay, if they're acting upon the object, that means that there's stuff happening, but we don't necessarily know if there's work being done. Okay, they could be balanced forces, and if the forces are balanced, then there's no work being done because there's no actual changes in the acceleration or there's no actual displacement. Okay. You can use this one in the definitions to find that out. And again, on this one, you're just going to need to take a list of your conservative versus non-conservative forces. Here's your chart. So again, on the chart, here's the initial stuff, here's the final stuff, and you are trying to find mechanical energy, which is not conserved. So in other words, if these two are the same number of squares filled in, then mechanical energy is conserved. So you take a look at the total amount of energy beforehand, the K and the P, don't worry about the work. If the energy is the same, then it's conserved. If the energy is not, it's different. So for example, chart A, energy is conserved. Chart B, energy is actually gained because you had 3 potential, and now you have a total of 5 in the energy. So you gained 2 by work. Okay, so just go through those and see if it's helpful to you. Okay. Consider the 3 situations below. In which situation would mechanical energy not be conserved? This is more of the applications. So keep in mind non-conservative versus conservative forces. Non-conservative forces, friction, air resistance. Okay, keep that in mind. And I can tell you, as a softball player slides in third base, there's probably a little bit of friction going on. Okay. Potential and kinetic energy, you can do the math on that, and basically you're going to be adding the total amount of energy plus the amount of work being done. Again, you're going to need to do the math on this one. The force applied parallel to an inclined plane, that means you don't need to worry about the cosine factor involved. Okay? And you need to figure out how much potential energy there was originally and add the amount of work, which would be the force times the distance. Again, similar math problem there. And then similar math problem here. Again, you guys can pretty much figure these out. Many of you can probably skip the YouTube videos. If it will be helpful to me to put the comments in the comment section, especially since I'll have a sub. Let me know if this is helpful to you, or if I need to write on the board or write on this doohickey macabre more, or that kind of thing. Thank you.